Okay, so paper 1 of the AQA Combined Science GCSE, the chemistry paper 1, sorry, has 5 topics in it, and this is the last of those 5 topics, energy changes. So where we're going to start actually is considering how we can tell whether a chemical reaction has taken place, and you'll understand why this is relevant in a second. So these are things I think that you did probably in year 7 or 8 and hopefully have come up again, but what signs are there that we can, or what observations can we make, sorry, that could tell us that a chemical reaction has taken place? Well, a classic example is that there's a change in colour. So if we look at an example reaction here, where we react magnesium with copper sulfate and we get copper and magnesium sulfate, we could clearly observe a colour change during this reaction because we start with the magnesium ribbon, which is a grey metal, or if we've sandpapered it, it might be a bit shiny and silvery. The copper sulfate, that's a very vivid blue colour, very strong blue colour. And then as the reaction proceeded, what we would see is we would see a reddish brown solid being formed, which was copper. And what we'd also see is the blue fade. So as the copper 2+ ions in the copper sulfate are reduced to copper atoms, we would see that blue colour fade, and the solution that's left behind, the magnesium sulfate, is colourless. So during the reaction, we would see the magnesium disappear. We would see a reddish brown solid, which is copper, appear, being formed, and we would see the blue of the solution fade, and if it went all the way to completion, it would fade to a colourless, and end up being colourless, sorry. So colour change is a classic way of telling whether a reaction's taken place or not. Another one is energy transfer, although you would have probably spoken about it much more in the sense of a change in temperature. Of course, energy transfers can be light, but if you see a flame, or if you see a light during the reaction appear, so with sodium and chlorine, for example, it gives a very strong, it glows very strongly, then we have an energy transfer. And given that's the title of our unit today, that obviously is going to be particularly relevant to what we're going to do carrying on. And so a change in temperature is going to be crucial. It's going to be one way, at least experimentally, that we can tell whether a reaction involves, well, in what way the energy transfer is, which will make more sense shortly. So classic example, I mean, a thing that you've done a number of times is you've used a Bunsen burner, and this is the chemical reaction that's taking place when you use a Bunsen burner. You've got methane, and it's reacting with oxygen, so this is a combustion reaction. It's producing carbon dioxide, it's producing water, and you know that there's an energy transfer taking place because, well, for a start, you can see the flame. So there's light, there's an energy transfer via light. But also the whole point of using the Bunsen burner is to heat something up. So that again is clearly a case of an energy transfer. You're doing it to heat something, so you're doing it so that there's a change in temperature. We might as well just carry on with the others. So a gas is produced as another piece of evidence. So again, thinking back to something else we've done in the course, in reactions of acids, you've done metal and acid producing a salt and hydrogen. So if you get in an exam question, sometimes you get asked sort of what would you observe during this reaction? And almost certainly, if they ask you that question, they will have given you the reaction equation and they will have given you the state symbols. If they ever give you the state symbols in an exam question, they are going to be relevant, they are going to be important. So they sometimes, like I say, they said, what would you observe, let's say in this instance here? So we could describe two things, or at least we could definitely describe two things from the equation itself. So we have a solid on the left-hand side, that's the magnesium, and we have no solid on the right-hand side, right? If you look at the state symbols. So we would see the magnesium disappear. Okay, so that's one observation we would make. So as the reaction took place, we would see the magnesium disappear. On the left-hand side, the reactants, we have no gas. But on the products side, we do have a gas, we have hydrogen gas. So we would see fizzing, we would see effervescence. So that would be a very clear observation, and we can see, we can tell this because we have a gas on the right and not on the left. So and it's in solution, so we would see the fizzing or bubbling in the solution. And one other observation they might allow as an answer in this, although it's not immediate, it's not really clear from the equation, although if you've done the reactions, you would have probably noticed it at the time, even if you've forgotten now, is that this would also involve an energy transfer. If we were doing this in a test tube and we had our hand around the test tube, what we would notice as the reaction was proceeding is we'd notice the test tube get warmer. So we'd notice that there was a change in temperature and therefore an energy transfer. And then the last one we're going to look at, which is less common at GCSE combined science, but if we have a precipitate or solid formed. So it probably makes more sense if I show you a reaction equation. So you'll notice on the left-hand side with the reactants, they are both aqueous. But you'll notice when you look at the products, we've got magnesium chloride, which is aqueous, but we have barium sulfate, which is a solid. So in the actual reaction, these would be two colorless solutions. And then when we added them together, the reaction took place, we would suddenly see this white precipitate formed. It would be very sudden and very noticeable. And so that's another sign that a reaction has taken place if you get a precipitate, or which is a solid being formed. So it means the solid is precipitating out of the solution. So we're going to be focusing from now on energy transfer, and there is going to be a practical aspect, but we're just going to understand about the fact that energy transfer can be in two different directions first. So we'll start with a reaction that hopefully you're very familiar with, which is respiration. So it's what you've done in biology. Again, you probably did it in years 7 and 8 as well as in your GCSE. And that is the reaction between glucose and oxygen to produce carbon dioxide and water. And this is a key reaction in life. And the reason it's so key is that it's a reaction that releases energy, which can then be used by the cells. So one of the whole points of respiration that you will have done is not only just what the reactants and the products are, but that energy has been released. That's been a key factor. I've got this word exothermic, which we're going to explain a little bit more shortly. But it's if energy is being released, that's what we call an exothermic reaction. And you can remember something going out or being released because it begins with X, like exit. So the energy is like exiting the chemical reaction, it's exiting the chemical reaction. We could also consider another reaction that you're familiar with, which is photosynthesis. And the reaction of photosynthesis is carbon dioxide plus water goes to glucose and oxygen. And we know that we require sunlight for photosynthesis to take place. And that sunlight is an energy transfer. And so what's happening here is that the reaction is taking place, but energy is being taken in. So you know that glucose, it's like a store, a chemical store. They're all chemical stores, but glucose in particular is the energy is being stored, if you like. And so the energy is being taken in, being stored, and we call that an endothermic reaction. But we're going to look at the definitions of these two terms very shortly. So one of the things that hopefully you've realized, or at least even if it's only on the previous slide, is that the respiration and photosynthesis equations are exactly the same equation, just happen to be in opposite directions. So if I'm writing it from having the reactants written initially as glucose and oxygen produces carbon dioxide and water, if we're going from left to right, then that is respiration. And we know that energy is released, and we've got that new term exothermic. If we're going from right to left, we know that energy is taken in. We know that's now we can call endothermic. So one of the things to take from this is that if you know the energy change of a reaction in one direction, you will now know the energy change of the reaction in the opposite direction. Okay, that's going to appear in some paper 2 topics, but it's a useful thing to sort of remember now. Whatever it is in one way, it's the exact opposite in the other way. Okay, so let's look at the actual terms exothermic and endothermic and how they're defined, although we've already sort of spoken about it already. So the way that we would describe what we mean by exothermic is that we're saying that energy is being transferred to the surroundings. So remember, this topic is called energy transfers, and in the case of exothermic reactions, the energy is being transferred to the surroundings. So ways that we can appreciate that that's happening is that if the temperature of the surroundings increases or rises, so things feel warmer or get warmer. And that's what we're going to look at in a second when we look at an example practical. And it has most reactions actually are exothermic, not all of them, but most of them. And they have has many uses. So just some everyday examples, because AQA wants you to think about everyday example uses. So fuels, clearly, that's the whole point, is that they release a lot of energy when they're burnt. There's self-heating cans, which perhaps aren't that common. And then hand warmers. So these are all examples, everyday uses of where we rely on an exothermic reaction. Endothermic, again, is about energy transfer, but it's the opposite direction. So instead of being to the surroundings, it's from the surroundings. And so a typical way of appreciating that is the temperature of the surroundings decreases or drops. So if you were holding on to something which was undergoing an endothermic reaction, what you might notice, or probably would notice, is that it felt colder. There is actually another way of spotting whether something is an endothermic reaction or not, and that is if you have to continually heat it or continually put energy in it for the reaction to keep going. So if I think of an example, it's baking a cake. So it's actually an endothermic reaction that's taking place when you're baking a sponge. And so you are putting it in the oven, and the oven has to keep, you have to keep the oven on. It has to be at that constant temperature for the cake to bake all the way to, if you like, completion, right? For the cake to be finished. If you took the cake mixture out part way through, or you turn the oven off, so you're stopping the supply of energy, or you're preventing the energy being put in, then the reaction essentially stops and your cake stops baking. So that's another example or another way of spotting whether a reaction is endothermic. So there are reactions called thermal decomposition reactions. So that's where you heat something up, and then as you heat it up, it breaks down into simpler parts, but they're called thermal because you have to put energy in to make it happen. If you were doing that and then stopped supplying the energy, that reaction would stop, and that is an example of an endothermic reaction. Everyday uses, there aren't terribly many obvious ones, and the ones that the AQA mentioned are sports injury packs. So they're those packs where you sort of snap them, the reaction starts, and it essentially turns into in effect an ice pack, even though it's not ice in it, but that's the essential purpose of it there. So there is a core practical in this topic. There are different versions of it, but they're all relying on the same principle, and it's really about you measuring a change in temperature and then drawing conclusions from that, measuring that change in temperature. So the example I'm going to use is zinc and copper sulfate producing copper and zinc sulfate. So just as earlier when we were looking at the colour change, we would see a colour change here. What would happen is the copper sulfate that blue would fade, and it would if the reaction, all of the copper sulfate reacted, we would find that then it just went colourless, and we would get that reddish brown copper being formed as well. Now the apparatus is not terribly sophisticated, but we use a polystyrene cup. And we would have a lid on it as well, and these are sort of key things to remember. So sometimes in exam questions they might have them in a beaker, in a glass beaker, and they might ask you what improvements could they make, or what improvement could the student make. And if they have got it in a glass beaker, and only a glass beaker, the reaction taking place only in a glass beaker, then one thing to do would be to replace it with a polystyrene cup or a lid. So it depends on how many marks they were giving. If it was 1 mark, probably both. Either of those answers would be acceptable. I'm slightly jumping ahead of the gun, but I just want to I just want to get across this thing about surroundings. So we've got a polystyrene cup, okay, and we've got a lid on it, and this, hopefully, you might have guessed that this is a thermometer. So this is a thermometer that's in the solution. And so this reaction is taking place. And if you think about what's here, I've written the reaction equation. So it's zinc and copper sulfate goes to copper plus zinc sulfate. But if we just look back to our state symbols, we've got aqueous on both sides. And of course, we've got a polystyrene cup. So basically, this is mostly water. So the thing to bear in mind is, yes, we've got copper sulfate, but even in that copper sulfate, the vast majority of it will be water molecules. And so this reaction takes place. Water does not feature in the reaction. Okay, water is the environment in which the reaction is taking place, which means that the water is the surroundings, or is the immediate surroundings. Okay, so when the energy is released, what's happening is that energy is being transferred, if you like, to the water molecules in the first instance. So they move more, so the temperature increases. So the reason we use a polystyrene cup for insulation is that we want to ensure that as much of the energy that's released by this reaction is solely in the solution, and because that is what we're measuring the temperature of. So using an insulated cup and a lid is trapping, if you like, as much of the energy in the solution as possible, energy that's released or taken in as possible, and so we're measuring the temperature of that, so we get a more accurate result. So please just remember and bear in mind having a lid and using a polystyrene cup. Okay, so I'm going to, if this is a practical, I've got to think about independent variables, got to think about dependent variables, got to think about control variables. So clearly the thing I'm going to be measuring is temperature. Okay, so that's my dependent variable. And what I'm going to be changing in this instance is how much zinc I add. Okay, so I'm going to do the practical a number of times with a different mass of zinc. So that means that's going to be my independent variable, how much zinc I add. So everything else has to be controlled. So one of the things I'm going to control is the volume of copper sulfate I add. So I'm always going to add 25 centimeters cubed. And the other thing I'm going to control is the concentration. So I've done a sum here so that we can see every time I am adding this number of moles to the polystyrene cup. But just to bear in mind, it's the same volume and the same concentration. So those are two control variables, right? The volume and concentration of copper sulfate are two control variables in this practical. And the thing that I'm going to change is the amount of, or the mass, sorry, not amount, I shouldn't use amount, the mass of zinc that I'm adding. So this is going to be my table. So the mass of zinc that I've added, I'm going to just record. This is not what you would normally find on a table of results, but I'm doing this to explain something shortly. So I'm going to translate or turn that mass into moles. I've got a starting temperature, I've got a final temperature, and therefore a change in temperature. And obviously, if I don't add any zinc, the temperature doesn't change, so I don't get any change in temperature. So now I'm going to start adding the zinc. So I'm going to start with 0.5 grams. So the reason I'm doing the moles is I want to just compare how many moles of zinc I'm reacting with the number of moles of copper sulfate. So I've always got this number of moles of copper sulfate. And if we look at our reaction equation, it's a 1-to-1 ratio. So if we compare this 0.0077 with the 0.025, we can see that the 0.025 is much bigger. So all of the zinc is going to be used up in this reaction. Okay, and then I've got a starting temperature, final temperature, and I can see what my temperature change is. And then I increase the mass again, and I increase the mass again. So, and if you look at these values of moles of zinc, you'll see that they are all less than the number of moles of copper, or the copper 2 plus ions, or the copper sulfate. So that means all of this zinc gets used up, and there would actually be a little bit of copper ions, a few copper ions left over. And we can see there's a difference in the change of temperature each time. Now, when I go to 2 grams, I've now got 0.031 moles of zinc, which is more than 0.025 moles of zinc. So what that means is, whereas on the 0.5, the 1 and 1.5, as soon as the zinc ran out, the reaction stopped. Now it's actually going to be as soon as the copper sulfate runs out, the reaction is going to stop. So I will be left with a little bit of zinc. I will have a bit of zinc left behind. So interestingly, the temperature change isn't as noticeable or as large as what it has been previously, and that's basically because once the zinc got to 0.025, there couldn't be any further reaction. There can't be a sort of more of the reactants reacting, so there's a limit. All right, there's a limit to the temperature change, and if we look at 2.5 grams, I've added even more moles of zinc, but because my copper 2 sulfate is limiting, it's a limiting reaction. It's limiting how much stuff can react. We don't actually get any change. That's just something to bear in mind. There is an introduction of limiting reactants or limiting reagents here. So we'll come back to that in a moment. So let's look at the change in temperature as I've increased the mass up to the point where I have more zinc than copper sulfate. Up to that point, we can see that the change in temperature is increasing. So there's an increase in the change in temperature. And in fact, just one of those results would have told me there was an increase in change in temperature. But anyway, so that means it's an exothermic reaction, right? Because the surroundings, which is the solution or the water really, and that's what we've got our thermometer in, that's what we're measuring, the temperature of the surroundings is increasing, which is why we get these higher final temperatures. And so that's an exothermic reaction. So we could draw a graph of that. And as I said at the beginning, my independent variable was how much zinc I was adding, and then my dependent variable was going to be what the change in the temperature was. Okay, that's the thing that's changing, okay, the change in temperature. And if I plotted those, my mass of zinc on the x-axis and my change in temperature on the y-axis, I would get a line that looked like this. And really, this is two lines, okay? This is there are two separate things to say about these. These are two separate lines. So it's quite possible in an exam question, if you either had to plot a graph or they gave you a graph, it would just be this slope or something like this slope. So let's talk about those two lines separately. So we have a constant gradient and it goes through the origin. This would be 0, by the way, okay, because we could see 0, 0, so no zinc added, no change in temperature. It's always a useful thing. They don't always give you the 0, so if you ever want to decide whether you need to go through, you should draw through the point of origin, or whether you have a point at the point of origin, ask yourself, if you don't have any change, if you don't add anything, would you get a change in temperature? And clearly the answer is no. So we call a line like that directly proportional. So the proportional bit is because we have our rate of increase is constant. It's because we have a constant gradient. So a gradient is our rate of increase and it's constant. So that makes it proportional. But what makes it directly proportional is the fact that the line goes through the origin. Okay, so that's a directly proportional line. This is completely separate, right? This horizontal line is completely separate. That is because it doesn't matter how much more zinc we add after whatever mass this point is here. The zinc is going to always be in excess. We can't have any more reaction by adding more zinc. So it's like this is where all of the copper sulfate is reacted, and it doesn't matter how much more zinc we add. It doesn't make any difference. So just think about that. Those are two different parts of the graph, and they just happen to be what I've got in my results. If you have any questions about that, just let me know. So we're going to look at reaction profiles. So this is another key part of the topic. They are basically graphs that tell the story of the reaction and tell the story of whether something's exothermic or endothermic. So we're going to look at exothermic reaction first. And so our x-axis here is just the progress of reaction, so in effect time, but we're not, these are more like sketches, so we're not really plotting things. They're just, they really are just basically sketches. So the progress of the reaction, so you can think about the origin being before the reactants are added, and then you can think about the much further to the right as being the reaction's finished and we only have the products. You will find, if you look in textbooks or CGP guide or whatever, and if you look at any graphs in exam questions, it'll just say energy on the y-axis. I've made it energy stored just because I think it's going to make it a little easier to understand. Because in physics, you've done energy stores and transfers, and one of the energy stores that you've done has been chemical store, and that's in effect what we're looking at here. We're comparing the chemical store with the reactants with the chemical store of the products. So if that's how we start in an exothermic reaction, the chemical store might look like this. What's important is that the reactants, the chemical store of the reactants is higher than the chemical store of the products. So that means when the reaction takes place, there is a change in the amount of energy stored. And if you also think of your physics and you think about the conservation of energy, you know that energy cannot be created or destroyed. It can only be transferred from one store to another. So what's happened during the course of the reaction is that the chemical store has decreased, right? That's essentially what this is showing us. The chemical store has decreased. Now, if the chemical store has decreased, that difference must have been transferred somewhere. Okay, it can't just vanish. Okay, we've got to account for it, and it's been transferred to the surroundings. Okay, so this is how we can think of why an exothermic reaction is working the way it is. So the chemical store of the reactants is greater than the products. That means during the course of the reaction, the chemical store decreases. Therefore, there has to be a transfer of energy, and the transfer is to the surroundings. Now, something else to bear in mind. If we think of an exothermic reaction, one we mentioned earlier was the Bunsen burner, combustion of methane. If we turn the gas tap on and we open the air hole so that we're getting a good mixture of methane and oxygen, the reaction doesn't happen. You have to do something to get the reaction to start to happen. So with a Bunsen burner, you have to bring a match to it, and it's only when you put the lit match to the mixture of methane and oxygen does the reaction start, and you get the flame, the Bunsen flame. Similarly, if you have a gas cooker, you can turn the gas on, but it's not until you flick a switch or whatever that produces a spark that the reaction starts. And so sometimes, and quite often, nearly always, and certainly probably GCSE, all the reactions that they'll ever do in this sort of context, you need to supply a little bit of energy in the first place to get the reaction to start. So it's like going over a hill, basically. It's like pushing the reaction over the hill. And so once you get to the top of the hill, it just naturally falls down to the end place, as it were, to the products. And so there is a name for the energy that needs to be required. So it's the difference between the store of the reactants and the sort of top of this hill. And this is called the activation energy. So it's the minimum energy needed to start a reaction. So in the case of your Bunsen burner, you have to bring a match. So that supplies the activation energy. In the case of your gas cooker, you have to have a spark. It could be some reactions you need to stir it, but basically there's something that needs to get the reaction going. So questions you can be asked to do with this is sometimes you can be asked to label or annotate a reaction diagram. Sometimes you're asked to sketch it, so they give you the axes and maybe just reactants, and you have to draw the products in the right place, either above or below. So obviously if it's an exothermic reaction, you put the products below. Okay, so let's see how an endothermic reaction profile compares. So the main difference or initial difference is that whereas with the exothermic, the chemical store of the reactants was greater than that of the products, here in an endothermic reaction, the chemical store of the products is greater than that of the reactants. So our chemical store is increasing during the course of the reaction. Our chemical store is increasing, If we have a change in that store, then we have to have a transfer. And so in this instance, the transfer is from the surroundings. So our chemical store is increased. That energy has to be transferred from somewhere, and it's transferred from the surroundings. And with our activation energy, the activation energy, you can see now it's effectively looks like a much bigger hill, right? So our activation energy, you've got to be very careful. It's from the sort of energy of the reactants all the way to the top of the hill. So it's a very similar reaction profile. So key things are, for endothermic, is that products are higher than reactants. And then the other key thing is the activation energy is from sort of the height of the reactants all the way to the top of the hill. And just remember that the change in energy is always the difference between the reactants and the products. Okay. Okay, so there's a final part to this topic. So you can think of it almost as almost in three parts. So the idea that there are exothermic and endothermic, and that we can do practicals where we measure a change in temperature. That's essentially the first part. Second part is the reaction profiles. And then the third part is looking at the energy change by focusing on the bonds that are broken and bonds that are made. So if there's a chemical reaction taking place, bonds have to be broken and new bonds have to be made. And the key part here is that energy is required to break bonds. So remember that whenever you've described any bonding, you've described it as an electrostatic attraction. So you are having to overcome that electrostatic attraction, right? So you've got to put energy in to break those bonds, to separate whatever the things that are attracted to each other. So energy is required to break bonds. And thinking back to our respiration photosynthesis, if you know what it is in one direction, you know it's the opposite in the other direction. So if I have to break a bond and it costs me Y energy, if I make that bond, I should get back Y energy. So energy is released when bonds are made. So energy has to be put in to break bonds, or energy is needed to break bonds, but energy is released or given out when bonds are made. And so in a reaction, you're breaking bonds and you're making bonds. And so the difference between the energy that was required to break the bonds that got broken and the energy that was released when the new bonds were made gives us the overall energy change of the reaction. And that could be exothermic or endothermic. So how we know which is that in an exothermic reaction, the energy that's released from forming the new bonds must be greater, must be bigger than the energy that was needed to break them. So it's, maybe we had to pay £10. It's like spending money. So we pay £10 to, obviously not to break the bonds, but we get £15 back. Okay, so that's how we can think of it with an exothermic reaction. But in an endothermic reaction, it's the other way around, that the energy we needed to break the existing bonds was greater than the energy released. So this time we paid our £10, but we only got £5 back. So we're going to be doing actual calculations, and so those are the descriptions about how we would explain our actual values that we're going to do in our calculation. So if we have a value that tells us it's exothermic because when we did the calculation, the energy released from forming the new bonds was greater than the energy needed to break the existing bonds, and then vice versa with an endothermic reaction. So now we're going on to bond energy calculations. So the thing is, not all bonds are equal, right? So it doesn't require, it's not the same amount of energy to break every type of bond. So every chemical bond has a particular bond energy associated with it. So some are easy to break, some are hard to break, and we can give them actual values. So here are just three different types of bonds. We've got hydrogen-hydrogen bond, we've got chlorine-chlorine bond, and we've got hydrogen and chlorine bond. And if we were looking at the bond energy values, these are the values here: 436 for hydrogen-hydrogen, 242 for chlorine-chlorine, and 431 for hydrogen-chlorine. So what that means is, if I want to break a mole, so it's got these units, kilojoules per moles, I wouldn't worry too much about it, but it basically means these numbers are to do with breaking a mole of these bonds. So if I wanted to break a mole of hydrogen bonds, it would need or require 436 kilojoules. If I wanted to break a mole of chlorine bonds, it would require 240 kilojoules. So one of the things that we can quickly see is that the hydrogen bond is stronger because it requires more energy to break than the chlorine bond. So now let's use those values in an actual reaction. So I'm going to use those 3 bonds. So we could react hydrogen and chlorine to make hydrogen chloride. One thing to do that makes life a lot easier is to turn these formulae into these displayed formulae that we have here. So we have 1 hydrogen molecule, we have 1 chlorine molecule, but we are making 2 hydrogen chloride molecules. Now the equation, if that's the right word, but this is all to do with what we said on the previous slide in words. If we want to know what the overall energy change is, it's going to be the total energy of the bonds broken minus the total energy of the bonds made. Okay, so we're going to apply this now to this particular reaction here, and so we've got the information that we need here. So for the reaction above, the bond's broken, so we are going to have to break this hydrogen bond, and we're going to have to break this chlorine bond, and there's only 1 of each of them, so it's going to be 436 plus 242. It's these 2 values here, and so it's going to cost 678 kilojoules. And then when we look at the bonds that are being made, there are 2 hydrogen chlorine molecules, so there's 2 bonds. So the bonds being made are 2 times 431 because we have 2 of these, right? We have 2 of these hydrogen chloride molecules. So we would get the energy that would be released is 862 kilojoules. So then we do the sum. So the overall energy change is the total energy of the bonds broken, so that's 678, minus the total energy of the bonds made, which is 862, and that gives a final answer of minus 184. Now, when you do these calculations, a negative value, a negative answer, means that the reaction is exothermic, and then a positive value means that the reaction is endothermic, and that's because the energy released is greater than the energy that was required to break the bonds in the first place. So in this particular reaction, we have an exothermic energy change. So one more example, a little bit more complicated, just to make life a little bit more tricky. So these are 4 different bonds. So we've got a carbon-hydrogen bond, oxygen-oxygen double bond, carbon-oxygen double bond, and an oxygen-hydrogen bond. These are the bond energies. So one thing we can conclude from this, for example, is this is a particularly strong bond. The carbon-oxygen double bond is particularly strong. That's a very large value, especially when we compare it to the other 3. We're going to do the reaction that's taking place when we use our Bunsen burner. So that's our methane and oxygen going to carbon dioxide and water. So we need to have a balanced equation. So we got our methane molecule, 2 oxygen molecules, carbon dioxide molecule, and 2 water molecules. Now, if you're given, and this would be a harder style of question, if you're just given it as formulae, then I very, very much recommend you draw out the displayed formulae for those molecules, because it's going to make your life a lot easier. So that's what methane looks like. Now, you haven't done that. That is something you do in the paper 2 content. You will learn about the structure of methane. So I appreciate that's not something you're aware of so much now. Oxygen, that we did do that with structure and bonding when we did dot and cross diagrams. So we had the double bond, we had 2 shared pairs of electrons, and carbon dioxide I think appeared in that as well, and so did water. So I'm not saying that you instantly remember them, but they are molecules that you would have done, dot and cross diagrams and displayed formulae of in your revision and work to do with structure and bonding when you did covalent bonding and simple molecules. Anyway, so there are it shows very clearly then we know how many of each bond there are. That's the reason for doing it. It's very obvious there are 4 carbon-hydrogen bonds in methane. And drawing both molecules of oxygen reminds us that there are 2 oxygen-oxygen double bonds being broken. So we do what we did on the previous thing. So we just focus on the bonds broken. We're breaking all of the bonds that are on the left-hand side. So we're breaking 4 carbon-hydrogen bonds, and we're breaking 2 oxygen-oxygen double bonds. So we add all of that up, and so we get 2,648. Just to say, oh, maybe I'll say it in a second, actually. Okay, sorry. If we think about bonds being made, we've got, and this is why it's useful to draw it, we can, even though it's one molecule, we have 2 carbon-oxygen double bonds. So 2 times 805. And the water, easy one to get caught out on, each water has 2 oxygen-hydrogen bonds, so we have 4 oxygen-hydrogen bonds. So we get our value for the bonds being made, and then we do our overall energy change. Bonds broken minus bonds made, we get minus 818, which is an exothermic reaction, which is what we expect because we know that using a Bunsen burner transfers energy to the surroundings because it's heating the surroundings up. So that's good. That makes sense. And the majority of reactions will be exothermic, but just be prepared for some endothermic ones. If this had been a positive number, that would have been an endothermic reaction. Now, the thing I just wanted to say is, and a question like this could be, the minimum number of marks it would be 3 marks. It's possible it would be slightly more, but let's just go with 3 marks. And thinking about how to get those 3 marks, if you looked at the mark scheme, it would be literally 1 mark for working out the total energy for bonds broken, 1 mark for the total energy of bonds made, and then the final mark for the energy change. So one of the things I want to stress is don't take shortcuts. Write out bonds broken, get it right. Write out bonds made, get it right, because then you've at least got 2 out of the 3 marks. And even then, if you mixed up which way round they were, you would still have got 2 out of 3. So please bear that in mind. And this reaction is clearly exothermic because we have the minus value. So that covers energy transfer. I hope that was clear. If you have any questions, please let me know. Thank you.